Hello and welcome back to D3D12Ez here on the Ludwig Fusel channel. In this video series we're gonna take a DirectX 12 on an ad hoc approach, doing everything step by step, learning just what we need at just the time that we need it. Now in today's video we're gonna continue on the pipeline state, and we wanna fill a few of these to-dos that I have quickly stated out. Now the goal of this video is to talk about the root signature and the rasterizer as well as the stream output, because they are not too complicated. The root signatures have like half complicated. These two are not complicated at all. These down here are also just required to zero them out, and then we're gonna have the full next video to do like blend state, def stencil state, sample, mask number, render targets, and all of that blending stuff that's a bit more involved. Now let's get started about today with the root signature. Now we haven't talked about the root signature yet at all of the concepts, so let me actually hop on the Microsoft documentation and show you a bit of an information on how root signatures work. Now the general idea of a root signature is to configure the application and the shader. So the general idea is the root signature is kind of like a set of arguments that tell the application how the shader's memory layout looks like, and also to tell the shader how it shall bound itself to memory. So the general idea is we have GPU memory. The GPU memory is directed by the CPU with comment lists. We basically tell the GPU to do certain operations on its memory. However, the memory is consumed and produced by the shader. So the CPU is kind of like the orchestrator, like the orchestration, the control plane kind of like thing. And since it is the control plane, it basically says allocate memory, use the memory for that thing, put the memory in that state, copy to that memory, and it's basically orchestrating how the memory shall look like and how we shall interact with the memory. On the other hand, we have the data plane, the actual shaders, the HLSL shaders that we have written. These are kind of like the workhorses that take the meta information from the control plane, from the so-called later on comment list and root signature, to then read data in a massive parallel way from memory and to write data to memory. So the shader is a workhorse. It's processing data and interacting with memory, reading something in, doing massive processing on that in a massive parallel way, and then writing it back to memory. And the control plane, our CPU, is directing how these operations shall work, which memory shall be accessed, which memory is currently not accessed, and it's basically telling how all of that comes together. Now, all of that is kind of like in a big topic called resource binding in DirectX 12. Resource binding in DirectX 12, it is basically a whole thing that talks about how binding works with like these descriptors and descriptor heaps that we have already talked about, these descriptor tables that we haven't talked about too much yet, and then like these root signatures. Now in general, like the root signature is basically the memory signature of a compute program on the GPU. So in the root signature, we basically define the resources that a shader needs to access. For example, the shader needs to access a texture or an array of textures, or it shall access an array of textures using an array of so-called samplers, or it shall access all textures with one certain sampler that helps him access the textures, or we tell it there is one buffer. So in general, all of the kind of like dynamic data that's bound, that is like kind of like not part of the pipeline, is described by the root signature. The root signature tells where these memory contents are located. And this is also something, or combined with something called resource binding. It is a resource binding on the GPU, and we do this by specifying root signatures. Now, root signatures can be created and specified in multiple ways. One way of specifying root signatures is through C++. You can see here's a bit of C++ code. We can describe root signatures using these descriptor ranges. This is like using D3D12, which is like a special library that makes access to these structs a bit easier. However, you can see that even if we are using like this library that makes accessing easier, you can see that this is a lot of code that we need to write to bind this. And actually the thing is that we need to write this multiple times. We need to bind this to the shader as well. If I scroll a bit up, you can see that binding to the shader in HLSL is done with the register keyword. We're gonna get to how this works in a second. So previously we had like these double points and then these semantic names to bind it to a semantic, and we also have double pointed and register, and in brackets some parameters to bind it to a register. So so that it's kind of like bound to memory and not to the pipeline. Now, in general, you need to do this in the shader and you need to do this in the root signature. And you can define these root signatures here in code. However, this is not the way of doing it. We do not want to specify this in here. Why do we not want to specify this in here in C++? Well, we don't want to specify it because it's kind of like hard-coded. We want to keep our shaders and our runtime code separated. And that's actually the thing, right? This is shader code, actually. We are describing the layout of the shader. Why should we do it in C++ and not inside of the shader itself? Well, we can do it in the shader itself. So we also have the option to specify root signatures in HLSL. So how do we specify them in HLSL? Well, we do it by a hashtag define. We do a hashtag define to define them, and later on in the shader, somewhere down here, is it showing it in here? It should tell us, yeah. And then later on we can use this hashtag define in a certain attribute before our main application is coming. We can use it in here. Root signature, my rs1, to kind of like bind the root signature to a shader. And the nice thing is, if it is bound to a shader, the DirectX shader compiler can do validation. And if the shader compiler can do validation, we already are getting some meta information on what's going on. And the nice thing is that we actually have the option to split off the root signature. This is kind of like the command to split off the root signature, right? You can basically tell it, all right, this is the input file, my root signature.hls. The entry point is called my rs1, which is basically the define, and the output file is this fxo or cso or however you wanna call the output file. And then if you're specifying this rootsig11 argument, you're going to get the root signature serialized in a binary blob that we can then use inside of C++ to load it on the CPU side. And that's what we want to do. This is a clean way of doing it. Now, how do these root signatures work? Well, basically what you are doing is you are designing the layout of memory. For example, you can say that we have a root CBV, which is a constant buffer view. And this constant buffer view, for example, is bound to the register B0 on the register space 1. So if you would want to access that, it would be, I don't know if it is already bound somewhere down here. If you want to access them in the shader, it's probably not shown in here, right? No, it's not shown in here, but if you would want to access them, we had the tab that I just closed, reopen close tab. In the shader itself, we would access it by B0, comma, or like, yeah, commata 1, because it's a different space. But we can use this with these indices in these register calls with like B for buffer. Now, you can kind of like see that you have this layout. This is kind of like the root layout. You basically define the layouts in here. For example, a constant buffer view, shader resource view, unordered access view, or a so-called descriptor table. A descriptor table is pointing to memory that is used for a descriptor heap. And inside of this descriptor heap, you can then manage a hell of a lot of array of data. And you can, for example, even like put in arrays of unknown sizes. So there are many options of doing this. You can combine static values. You can combine static root level constant buffer views, shader resource view, and unordered access views that are accessing the resources, as well as a list of descriptors that are also like specifying something. And a big important thing to note on these root signatures is that one on the left here, this is actually some constant memory. I don't know how big it is. There is a certain limitation to it. It is basically a certain blob of memory that's always like allocated with each shader and also available per like, let's say, per like core that is kind of like executing the values, so that addressing works, right? Because addressing basically works like that. Addressing works access a shader resource view at index 1. And then the GPU knows where to read the meta information from the root signature and then knows which memory to access. Or if it is a descriptor table, you're kind of like going there with like a pointer. So there's a bit of pointer indirection here so the GPU can see, all right, slot 3. At index whatever, it is a descriptor table, alright, so give me the address of the descriptor table, then offset the address to the array index, go in here, take the correct descriptor, know how to access the memory. This is in general how it works. Samplers work a bit different and Hewins also work a bit different, but this is going to be way clearer as soon as we are getting to it and we are playing around with these features. That's kind of like the idea. We're going to play around with these a lot as soon as we are getting a bit of rendering going so they can understand them. However, what I want to do is I want to define the root signature, and you can see that these root signatures are, I think this one is the correct one for that one. This is kind of like how you define them, and this is kind of like the layout that's going to result, right? Constant buffer view B0 space 1, constant buffer view B0 space 1, shader resource via texture null, texture 0, UAV, and with a bit of flex. So in general, you have like many options to define them. However, we want to have a minimal one. So let's go into Visual Studio and define the most minimal one that we can do. So first of all, I want to go to my shaders. I want to add a new item, and you can see that as soon as we go to HLSL, we don't have a way for specifying the root signature. I'm going to take the HLSI header file, and we're going to modify it so that it compiles. I hope that we have options available. Maybe we need to discard the I so that the shader compiler, we probably need to remove them. But yeah, let's maybe call it root signature.hls. No, like that. There we go. And now we have the root signature, and the idea here is now, I can see maybe I can get it to work with the HLSL compiler without changing it or changing it to include. So in general, what you want to do is you want to have a root signature, shader model root signature 1.1, and this is basically telling you to export the root signature. Now the entry point, I'm going to change this to root sig. This is how I like to call it for root signature. If you have multiple of them, you can give them different names like root signature pass 1. And then you have kind of like root signatures that are named to your render passes that you have. However, I'm just going to call it plain root sig. And what I can now do is hashtag define, not root signature, root sig. And then the general idea is that we now have a macro where we can define all the properties that the root signature shall have. Now, if we go in here, you can see that these are all like in quotation marks. So the root signature is actually a string. So let's specify it as a string, and I tend to do it like that. Right, so what do we want to specify? Well, we do not want to have all of these bindings. We're going to have a completely empty root signature with no bindings in it. So the only thing that we need is we need the root flags. Now, what are root flags? Well, it's actually quite simple. You just need to know the enumeration, how to find them. Root flags, or D3D12 root signature flags. There it is, already one. So the general idea is this is the enumeration. Root signature flag none, allow import, assembler input layout, then a vertex shader root access, and all of these data. For example, you can deny shaders accessing the root signature. You can allow the stream output. You can deny with some other stuff, and you can have like multiple flags that are maybe relevant. Now, the one important thing is that you're not going to prefix them. You can see that there's no prefix. You always need to discard the prefix. This prefix, D3D12 root signature flag, this is a prefix that's just used for C++. So we want to discard it. We just take what's behind it. So allow input assembler layout. And then you can see it works the same like C++. You can use the dash here as a OR combination of multiple flags. However, we're just going to have one because we want to have all shaders access to the root signature. So I'm just going to specify this one single flag. And then if I would go further, I could further specify something with a comma here to indicate that there are more data coming. So if I would have something more, I would have the comma here. But since I just want to have the flag because we don't bind something yet, I'm just going to leave it empty like that, which is basically going to show how it works. And now a very important thing that I think is the most important with your root signatures is to define a table. I don't need that, this is oxygen. So the most important thing is that you know how your root signature is laid out. And this is why I always give it a bit of a comment here. And then I specify the layout with the like texture layout, T0 to infinity is that certain thing, and I specify how it's laid out. However, since we do not have a layout, this comment is empty. However, I would highly recommend that you always do comments, because these root signatures, as you can see, they grow complex and you just see how many descriptors are in there and what type of descriptors there are. And what is really important later on if you're working with shaders and if you are working with C++ is that you assign them and that you are using them correctly. This is why I always document everything, how it's kind of like intended and laid out. So basically I define this is how it shall look. These are the registers that are bound to the certain resource type, with the following kind of like usage that we want to have. And then I say these are the binding slots for C++, and then I have a nice comment that I can always take a look at without a need to try to interpret what this means. So that's what I recommend. Most simple root signature that you can have. Let's now integrate that. So how do we integrate it? We're going to go to our shader. The first thing that we need to do is we need to include it. And I'm going to include, it's sadly not autocomplete, root signature.HLSL. Normally you would have an HLSLI for includes, but I think the root signature is fine. There's no applications in here, so we shouldn't have an issue, right? It's not 100% clean, but since this needs to be fed into the compiler, as far as I know, Visual Studio has a problem with HLSLIs and not enables compiler access to them, even though it would work. Yeah, I would just recommend doing it like that. Alright, so root signature.HLSL is now basically included, and now we just need to use it. Root signature. I'm binding a root signature, root sig. And now I have bound the root signature to the shader. And I can do that also for the, what was that? This is the pixel shader for the vertex shader.HLSL. I can also go in here and I can specify root signature.HLSL, and boom, there we are. If we now will quickly hit a recompile, let's see if everything works. All right. Now output provided for debug. Okay, so we have a problem here with which shader? Let's see. Root sig entry point not found. So this was for what? We can see what was compiled. Let's see if I compile a pixel shader, does that succeed? Yeah, pixel shader succeeds, vertex shader succeeds. Warning, yeah, it has a warning, but that's not an issue. If I compile the root signature, all right. So the root signature fails. Root sig. This is actually the name. Let me quickly see. We might need to think a bit around with that. Set root signature preprocessor. We might need to go to a certain thing, but normally this should be actually fine. Quite sure why it doesn't do what it should do. You could just also leave the entry point empty. This might also allow it to compile. No, it does not. Well, that's interesting. But we can find this out simply by going to my other project here that uses the same layout. Root signature. Root signature.HLSL. Shader condition. Shader type is the root signature, and this is the... Okay, so we need to set the shader type to root signature. How can we set this shader type to root signature? Ah, there it is, shader type. Ah, okay. Right. If you just need to read, generate root signature object. This is what you want to generate a root signature, and the entry point is root sig. And now I should have the correct parameters to compiled it. All right, so now it has been compiled. Now we have a root signature.csl compiled shader object as an output, because the root signature is kind of like a shader, even though it is not. The root signature is basically a non-intact shader. This is an intact shader. It has an entry point and the root signature attached to it, and the other one, the root signature itself, it is not a intact shader, it's just a shader with a root signature basically. But now we have the root signature in here. Now we can use the root signature to read it in here. And yes, the root signature is a shader, which is not 100% ideal. Root signature. Root signature. And now we have the root signature loaded. And now I need to compile that. Maybe I'm gonna call this one root signature shader. Let's call it root signature shader. And then what we want to do is create root signature. So from the root signature shader, I want to create now a root signature object. So root signature object is a com pointer to an ID 3D12 root signature. I don't think that there are special ones of them. No, there's just a plain old root signature. And this is now the good old root signature that we want to output. And how do we compile a root signature? It's actually not that hard. dx context get, and then we have a get device, so that we get our device, and then we can create a root signature. And how do we create a root signature? With a node mask. Then we need a blob with the root signature, which is the get buffer one. So let's get the buffer here. Then we need the length of it, get size. Then we need IID PPV args to our object that we want to have, which is the root signature. I don't think that we have done some error checkings in here. Do we have done error checkings? No, we don't. All right, so this is basically how you create a root signature, right? You're writing the root signature here in hashtag define. You need to know how to configure your compiler properly and your IDE properly. And if this is done correctly, it's producing an output. And you can bind the root signature to a shader using this signature. And then the root signature is bind. And the root signature basically defines how resources are bound to your shader. Now, inside of main, you can read the root signature by reading the file into memory, basically the binary data, just as is. And then down here with the create root signature flag, by just providing get buffer and get size and the node of where we want to create it, you can create a root signature. It's no rocket science, it's actually darn old simple. And binding it to the pipeline state description is also the most simple one. P root signature equals root signature. There we go. And it's bound. Because I actually have an operator that's converting the com pointer to a plain DirectX pointer. But you can see, as simple as that, bound to the pipeline state, read it into memory here. If I now hit F5, make a breakpoint here, I'm on debug, that's correct, and I should validate that my root signature is fine. And if I go in here, let's go in here, it's a bit easier to see for you. There you can see the root signature has a pointer, a valid pointer, we don't have an issue. So they was actually able to read that compiled root signature, even through that the kind of like usage with like this, seeing it as a shader and having it as a hashtag define, and this hashtag define being compiled in a binary object, which is kind of like a bit odd. But it is as it is, and this is how it works. Alright, so let's continue on now and talk about the rasterizer state and the stream output. Let's talk about the stream output first, or no, let's talk about the rasterizer state first, because this is the one that's a bit complicated, but not complicated at all. Because the rasterizer state, well, it has many options available, but in it itself, it is not too hard to use. Let's peek in here and let's get all the parameters out so that we can get a bit of a meta information on that, and then I'm gonna do a bit of information. Was that? No, this was not formatted, sadly. So let's remove all of that clutter. Oh, that's not what I wanted to do. There we go. Let's remove the clutter here, and then we can get this up and running. Then we can talk about how these parameters work and how this is all laid out. Now, in general, I would have been prepared for that, but I think it's also important to show you documentation, and I have not done that recently in the videos. But actually, it's simple, right? Documentation, Microsoft, they are definitely giving you an information on how everything works. They are pointing you out in the right direction. They are giving you some logic that's behind the scenes, and this is everything that you need to know. Microsoft documentation, search for the struct that you want to fill, and you're going to get all information that you need. But let's first get started with the two simple ones in code here. So the first one is the fill mode that we want to specify. Now DirectX 12 and the Rasterizer supports two fill modes, solid filling and wireframe. And this is actually easy. If you have a triangle and you're using solid filling, then basically the whole area of the triangle is rasterized to pixels. If you're using wireframe, you're basically not filling the triangles, you're basically just gonna color in the lines, connecting the vertices. We want to do a solid rendering, so we put it to solid rendering. Now the next thing is that we want to do is the cull mode. Culling is used for backface and front face culling. We don't want to use culling yet. We're going to talk about culling when we have the problem that requires culling. This is why we set it to none, which basically means disable culling. Now the next thing that we have is front counterclockwise. Front counterclockwise is something that has something to do with culling and how front and back phases of cullings are producers, and that's basically inverting the logic. We don't need that. That's why we set it to false. The next ones, the next three actually, are related to depth biasing. Depth biasing means offsetting the depth values, which we haven't talked about yet and won't talk about too much yet. In general, the depth biasing is offsetting a certain value of your triangles. That's been computed from the rasterizer. And the rasterizer is basically, before it's rasterizing it, it's kind of like pushing your triangle forward. That's basically what depth biasing is doing. Since we don't want to do that, we're going to set all of this depth biasing to 0. I think this is a float, right? No, this is an int, and these other two are floats. No, int. And this is a float. Yeah, right. So int 0 and 0, or was it a float as well, and I was just an idiot. Yeah, okay. So .0f and .0f, which basically means no depth biasing. The next one is depth clip. Depth clipping is enable clipping based on depth distance, and you can see the logic that's going on here for depth clipping. We do not want to use it currently. Yeah, so we're gonna put it to false. So also advanced. Multi-sampling, we're also not gonna use multi-sampling, so we put it to false. Anti-alias lines, we're not gonna use line rendering, so we put it to 0. And the last thing that we need is the voice sample count, and you can basically specify 4 UAV rendering or rasterizing to voice sample counts of 0, 1, 4, 8, and 16. However, we don't want to use that voicing, so we put it to 0. This is kind of like a default description. Again, these are all things that you don't need to understand yet. What you need to understand is fill mode. That's like the most only thing that you need to understand currently. This culling is something that we're going to talk about in a special video. Depth bias is where we're going to talk about in a special video, where we're going to talk about decals. Decals is a very nice thing in rendering that makes your game kick, that makes a game awesome, that makes your rendering awesome without having graphical issues, and this requires depth biasing, but that's something that we're going to talk about in the future. Depth clipping is also something that's kind of like related to all of these things, but kind of like independent, and can be also used completely independent. Then we have multi-sampling, anti-aliasing for lines, and sample counts for multi-sampling and UAV and stuff, and we don't need that yet. Really, we don't need it. The rasterizer, the only thing that's really important that we need to set is that we use solid mode here and that we don't use culling. Because actually the cull mode none is actually not the default one as far as I'm concerned. I think the default one is backphase. Well, actually, there is no default one. So if you're zero memorying that, you're gonna have a bigger problem. That's the general idea, right? Okay. This is why we also want to fill these, because this can really result to problems if you don't fill it out completely. Speaking about that, let's continue on with the other things. We're going to want to fill out the stream output. The stream output has many things that are described here. First of all, you have num entries and num strides, as well as the buffer for strides and the buffer for entries. And if we put them to 0, because we don't want to use the stream output, so we're not going to have entries and we're not going to have strides, then we can put our strides buffer to null pointer, and we can put our declarations to null pointer, which are the entries. The only thing that's then used here is the rasterized stream, and I think, what is the rasterized stream? Let's peek in here. This is probably, it is a uint, so it's kind of like a index where you might want to raster out. Yeah, we don't use it, so 0. This is kind of like the general idea. Don't use it, put it to 0, and you are fine. Now, there are a few more things that we need to put to 0. First of all, we have a bit of a shader problem. Vertex shader and pixel shader are specified, however, all the other shaders are not. specified currently. What are the other shaders that we need to specify? VSPS is here. So we have DS, HS, and GS. So these 3 ones, these also need to be specified, or I want to specify them would be the correct way, because it might not be required that you fill them in. However, DirectX is sometimes a bit hard, because some of these values might at some point be non-default at 0. And this is why we want to always make sure that if we have complicated structs like that, that we always set all members, because 0 does not by default mean default. This is why there's like D3DX that helps you doing this stuff, but using a helper library without understanding how this works and without understanding why your code in comparison if you're using a library does not work, it's not really something that helps. So we rather want to specify everything on our own. Right? That's kind of like my philosophy on that. Now let's quickly fill out these 3 things so that we have a full video next time for blend state and binding that to a command line, and maybe also rendering next video. So yeah, node mask, cached PSO, and flags. These are actually simple values to set, because node mask, we always set these to 0 to basically say here's the default GPU. We are not aware of multi-GPU rendering. Cached PSO, it basically means loading a PSO, a pipeline state, from a binary. So basically what you can do is you can take all of these shaders, you can take all of these control values, and you can compile them into a binary state. This binary state is dependent on your GPU, because basically these bytecodes, these are DirectX intermediate layer bytecodes, and they are sent to kind of like the driver to compile it into native code of the GPU, but you have an option to read this native code back. So often what games with many shaders and many pipeline states do is when the game starts the first time, you might see in the loading screen a text called compiling shaders, because this is basically executing these steps, or maybe even a proper shader compile depending on optimizations on your PC. And it's basically putting them into these descriptors, constructing these descriptors, compiling these descriptors to a binary blob that can be on later runs of your application, of your game being loaded. That's the general idea here, but we don't need that. So size 0, and cache blob is null pointer. Next thing that we need to specify are the flags. These are just some flags over how we are using the pipeline state. You can have none and tool debug. I'm just always going to put this to none, because we don't really need that. That tool debug is something advanced. And now you can see that our pipeline state is already looking quite long, but already looking good, right? We can understand all of these. Root signature, we have talked about this in that video. Input layout, we know how this works. Index buffer stripe cut, we know that we don't want to use it. We know how to attach our shaders into it. We might not use certain of them. And I should have used null pointer at these pointer values, right? There we go. Then we have fill mode and cull mode. That's also quite simple. Solid, non-culling, front counterclockwise. These are all things that we don't use, so that's set to none and false. Depth biasing, we don't use it, so it's 0. Clipping, no, we don't use it, so it's false. Multisampling, don't use it, it's false. Anti-aliasing for lines, we don't use it, it's false. For sample count, we don't use it, it's false. Stream output, everything is null pointer or 0, so we don't use it. Node mask, default GPU, cached PSO, 0 null pointer, we don't use it. Flags set to none, because we don't use it. It's really not that complicated if you are getting a hang of the concepts. The blend state and these stuff, this is going to be a bit more involved next video then, because these one are also kind of like escalating quickly. But that's the general idea, right? It is a big descriptor that is describing a hell of a lot of stuff. But in general, you just need to know what you need to know. And this is why we're doing it ad hoc and step by step with the shaders, root signatures, and what we need to do to get the code running. So thank you for watching. See you in the next video. Make sure to like and subscribe, and have a nice day. Bye.